Hi, I'm Nicholas Twerk, and today we're going to discuss the subderivative. The power set of a set, denoted by a script P, takes a set as input and returns all subsets of the input. For example, if B is equal to the set 1, 2, 3, then the power set of B is the empty set, followed by the sets containing 1, 2, and 3 individually, followed by the sets containing all pairs 1, 2, 1, 3, and 2, 3, and then B itself, 1, 2, 3. Consider the function that maps a set to its power set. This is a set-valued function. Every output is a set. Let f be a function that maps the real numbers to the real numbers such that f is convex and differentiable. Then g, which is a line approximating the function f locally, equal to f of x plus f prime of x times y minus x, is a global underestimator of f. What does that mean? That means that g of y is less than or equal to f of y for all y. And here's an example. F is the solid line, g is the dashed line, it's the tangent line at the solid dot, and you see that it is less than or equal to f at all locations. Now let f be a function that maps the real numbers to the real numbers such that f is just convex. It is no longer differentiable. Then theta is a subderivative of f means that g of y equal to f of x plus theta times y minus x is a global underestimator of f. And you see the relationship here. We've replaced f prime of x when f was differentiable by theta. So the subderivative is a generalization of the derivative. When f is differentiable, the only subderivative is the derivative. If f is convex but not differentiable, we will have many subderivatives. Here's an example. In the solid line, I'm plotting f of x is equal to the magnitude of x, and the dashed lines all show global underestimators of f at x equals 0. The slope of each of these dashed lines is a subderivative of f at x equals 0. Definition: the subdifferential of f, which maps the real numbers to the real numbers, is the function partial f that maps the real numbers to the power set of the real numbers, such that the partial of f of x is the set of all subderivatives at x. Here's an example. F of x is equal to the magnitude of x. Then the subdifferential of f at x is equal to the set containing -1 if x is less than 0, the set containing 1 if x is greater than 0, and the closed interval between -1 and 1 when x is equal to 0. So this is a set-valued function. A subdifferentiable function is one where the subderivative exists at all elements of its domain. With differentiable functions, remember, we knew we were at a local extremum when the derivative was 0. The analogous statement with subdifferentiable functions is as follows. With subdifferentiable functions, x is a local minimum of f whenever 0 is in the subdifferential of f at x. We can use the subderivative to find a local minimum of a function similar to how we used the derivative, and this will be called the subderivative method. The inputs are our initial guess x naught, the step size alpha, which is greater than 0, and m, which is going to be greater than 0, and we'll see what m is in a second. We set x to our initial guess. We also set x best to our initial guess. X best is going to be the value that gives us the best outcome so far. And fx best is going to be the value of that function. It's going to be f evaluated at x best. Here's our loop, and we'll talk about the stopping criteria in a minute. These are the iterations of the loop. We find a subderivative g. We perform a subderivative update, which it looks exactly like the derivative update, x is equal to x minus alpha g. And then we evaluate our function at that point x. If f of x is less than fx best, so if fx is better than the best thing we've seen so far, we update our best variables. Now let's talk about the stopping criteria. We create this variable fx best not updated. This is going to keep track of how many iterations we've run where we have not updated fx best. We're going to iterate until we've not updated fx best for m iterations. So if we run m times in a row and don't find anything better than what we've already got, we're going to exit. So down below, if fx is less than fx best, then we update the best variables. We also set fx best not updated to 0. Otherwise, we increment fx best not updated, and then this function returns x. So why do we need to keep track of how many times it's been since we updated fx best? And the answer is because we could get stuck. Here's a simple example. With a constant step size, we will not converge to a solution. The most that we can say is that we will get close to a solution. And the smaller the alpha, the closer we can get. But here's an example where we're optimizing the magnitude of x. You can see that when we get close to an optimal point, maybe we're at the left arrow of the dashed line, and the subderivative method will move us all the way to the right arrow of the dashed line. And then the subderivative method would move us right back, and it'll just bounce back and forth between those 2 points. So if we do that m times, then we exit the iterations. We can modify this to converge to a solution. We have to change the step sizes. One way to do it is by changing the step sizes so that they satisfy the limit as k goes to infinity of alpha sub k is equal to 0. Here k is the iteration number. And the sum as k goes from 1 to infinity of alpha sub k is equal to infinity. That means it's not summable. So for example, alpha k equals 1 over k satisfies this. It goes to 0, but it is not summable. This will converge to a solution, but it can take an extremely long time to get close. And this would require a different stopping criteria than we previously had. Why? It's going to consistently improve the best estimate with iteration number. It's not a descent method. It won't guarantee an improved function value with each iteration, but over time it will get closer and closer to the optimal solution. One way to solve this is just to set a specific number of iterations. Definition: a proper convex function is a convex function with a range of the augmented reals, the real numbers with infinity. Let f and g be proper convex functions where f is differentiable. Then the subdifferential of f plus g evaluated at x is equal to the derivative of f at x plus the subdifferential of g at x. For example, if h of x is equal to x squared plus the magnitude of x, we can call f of x equal to x squared and g of x equal to the magnitude of x, and then the subdifferential of h at x is equal to 2x plus the subdifferential of the magnitude of x. Now that we have an understanding of the subderivative, we're going to use it to find the minimum in an interval. Let g be a subderivative of convex function f, which maps the interval ab to the real numbers. If g is greater than 0, then for any y, we know that f of y is greater than or equal to the global underestimator line, f of x plus g times y minus x, which is greater than f of x. Now, why is this greater than f of x? Well, because y minus x is positive, since y is greater than x. And we know that g is greater than 0 by supposition. Therefore, g times y minus x is positive. Therefore, f of x plus g times y minus x has got to be greater than f of x. Similarly, if g is less than 0, then for any y less than x, we also have f of y is greater than f of x. So we can use this with the bisection method to find a minimum. If g is greater than 0, then we can eliminate the right half of the interval. And if g is less than 0, we can eliminate the left half of the interval. It eliminates half of the interval in each iteration, so it's faster than golden section search, which only eliminated a third of the interval in each iteration. That does it for this lecture. Thank you for your attention.